Welcome to this Artificial Intelligence and Autonomous Driving course. For the introduction of this course, I want to teach you the most fundamental idea of the algorithms behind artificial intelligence. These algorithms are known in mathematics as machine learning algorithms. So, in this video, I will start introducing the easiest example in this field, which is a simple graph that learns how to solve a given task, and then I will evolve such a graph into a more complex example that can be used as our first attempt to address the autonomous driving problem. So hopefully through this video you will learn the essence of learning in machine learning. What do we mean when we say that an algorithm has learned to solve a problem? And what is the mathematical intuition or the mathematical correlate of learning, which is of course a cognitive function of the brain? Welcome. Let's suppose we have a black box which represents a machine learning algorithm. We do not know yet anything about its internal operations. We only know that it has two inputs and one output. And we want our black box to respond with the right output to a given pair of inputs. Now, let's see a particular example. Suppose that the inputs in this case are 2 and 3 respectively, and the output we're looking for is 10. Well, to get our black box to respond accordingly, we need to open the box and see what's going on inside. Once we do that, we then find that in order to produce an output, the box internally multiplies the inputs, the two inputs, by some still unknown numbers. And the results of such multiplications are added together to finally obtain the output. So the inside of the box is a very simple graph that processes the inputs, applying some operations on them to finally output a number. Now, in light of this, we just need to find out the values of these two unknowns. This is what is the pair of numbers that satisfy this whole operation, so that given the inputs 2 and 3, the output produced is 10. So at this point, this can be seen as a guessing game. For example, if we put 0 and 0, a pair of zeros, what we will get is 2 times 0, 3 times 0, 0 plus 0 is 0. So our black box will not be responding as we expected. After some thinking, however, we can see clearly that if we put here a number 2 and here we use another number 2, these two numbers will satisfy our demand. 2 times 2 is 4, and 3 times 2 is 6. 4 plus 6 makes 10, which is exactly the output we are looking for. So finding these two numbers is what we call in machine learning fine-tuning or training. And only when we find the exact numbers that satisfy my requirements of outputs and inputs, an algorithm is said to have learned a task. Now, notice, of course, that if the inputs and the output change, So will these numbers we're looking for. And of course, in a typical problem of machine learning, we will have thousands and thousands of different inputs and corresponding outputs to be learned. So in that case, the training will consist in finding a pair of numbers that in average will satisfy the best possible every couple of input output. Of course, in most cases, there's not such a thing as an exact solution to this problem. This is, no pair of numbers will satisfy exactly the output for every single input. But then again, the task is to find those numbers that in average produce a minimum error between the actual outputs and the outputs I am expecting or looking for. Also, as I mentioned, this is perhaps the most simple example, but in most real problems, not only we have many inputs, but also each of those inputs will have millions, perhaps billions of components, not only two, as in this example. Therefore, the amount of numbers or unknowns that we will have to fine-tune will be really, really huge. That is why we cannot play a guessing game during training in machine learning, but instead, we will need to use a heuristic procedure in order to train our algorithm. Now we are going to see how all this translates into a more complex problem, such as self-driving. Here we have a good example. This is a car with a camera on top, which is capturing images. These are three examples of different scenes captured by the camera. In the first image, we see the road indicating the car that a turn to the left is needed, while in the second image, the road tells the car that it must continue straight. But in the third scene, we see that the road takes a turn to the right and therefore the car must follow that way. Since our graph or learning algorithm is expected to drive the car according to the information provided by the camera, these images have to be fed into the algorithm as inputs. To do so, we will first segment the road, removing all the background. Once the images are segmented, we will also drop their sizes so they become easier to be processed in this example. Let's take their sizes down to 23 by 23 pixels only. Now, we will also binarize each image by representing black with zeros and white with numbers 1. Also, we have to label each image, and the label will be our expected output for the algorithm. For example, this image, which represents a turn to the left, will be labeled as 1, 0. Next, we need to reshape the image so we can get a column vector out of this matrix of binary numbers. All we need to do is to stack every row of the matrix as a column, one by one on top of the other, until we get a single column vector to be fed into the algorithm. Next, as we did in the previous example, this input will be multiplied by a series of numbers and the results will be added together. Notice that the numbers I'm going to use are totally random at the beginning, but also notice that I'm going to use a second set of random numbers, so my graph will have two outputs. This is as many outputs as the labels. Now remember that the output I'm looking for in this example is the label 1, 0, which stands for turn to the left. But notice that when I apply all the multiplications and the additions, the result is going to be different. In this case, it's going to be 1 and 1, which means that the algorithm is not trained yet to resolve this task. Well, now we can try with another image. The second image is the straight image, which will have the label 0 and 0, which means straight. So again, if we try the same random numbers as in the previous examples, we will expect the algorithm to respond to this input, to this image, with a 0 and 0, which is the corresponding label. But unfortunately, again, we will see that the answer, after performing all these operations, will be also 1 and 1, meaning that the algorithm doesn't know how to answer well when it is presented with this image. Now let's going to try the third image, which is a turn to the right. You see the image here totally binarized, and the label is 0 and 1, is opposite to the turn to the left. Now we will expect our algorithm that when presented with this input, after all these operations have been performed, the answer or the output will correspond with the expected label 0 and 1. But unfortunately, for this input, the algorithm is also answering with 1 and 1, meaning that none of the images has been learned by the algorithm so far, and meaning also that these numbers are going to be fine-tuned. The algorithm needs training. Okay, we can also evaluate our algorithm. As you can see here, the number of expected outputs that are 3, and then also the number of successful answers or outputs provided by the algorithm, that in this case were 0. So 0 over 3 is equal to 0, which means that the algorithm so far is 0% efficient, because none of the answers, none of the outputs corresponded to the actual output, to the expected output that I was looking for. Now we are going to train the algorithm after many trial and error iterations. We will get a new set of numbers. You will see here that these numbers are going to change. These are the new set of numbers, and the orange numbers are going to change too, and we will obtain a new set of numbers. Now with these new sets of numbers, we can try again the 3 different inputs and see what's the result. So the first input, which label is 1, 0, it's organized here again as a column vector, is fed into the algorithm. All the multiplications and the additions are performed, and we expect to have 1, 0, and that is exactly what we now are getting after the processing of the input. Now this means that the algorithm has learned this particular image. But now we are going to try the second image, because it might be possible that these numbers work well for the first image, but not for the second one, for the straight one. So the label here is 0, 0. We still continue to use the same numbers as in the previous examples. We apply the operations, and we expect to have 0 and 0. But actually, okay, what we got is 0 and 0 after we perform all these multiplications. That's the result, meaning that this second image has already been learned by our algorithm, and we still have a third image to test our algorithm. And this is the third image, is turned to the right, which is labeled 0 and 1. Here is the input as a column vector, and our expectation is 0 and 1, as the label says. And now when we process the input, we will obtain the same label we were looking for, meaning that our algorithm, these two sets of numbers, are the proper numbers for our algorithm to learn or to respond correctly to each of our three images. Now we can evaluate again the algorithm, and we will see that now we have three cases, and the expected outputs were in all the cases equal to the actual outputs. So we have three successful cases. That's 3 over 3, 1, meaning that our algorithm is now 100% efficient.